All right, it is noon, so let's get started. Yeah, it's a cold and dreary day here in Troy, so I guess it's good to stay home or in some other warm place and maybe fix yourself a cup of your favorite hot beverage and organize some computers. So, welcome to lecture 21. How you folks are doing? Good, good. It's good to hear that decent. I take it as something positive. Tired. Yeah, heavy rain. Exhausted. Yeah, I'm with you. Still working on the homework. Yeah, you can do that. You can use your late days. So the deadline was last night. The extended, the modified deadline. But if you have saved or earned enough late days, you can totally use them. Remember, just one thing, you can only use up to two. Speaking of the homework, how am I supposed to format how MIPS code prints in add sub specifically? It should be specified in their PDF, but if you have any doubts, it would be best to just ask on the Submiti forum. Some students have been very helpful on the Submiti forum. And even posting their own little tricks on how to test code more conveniently. And this is, of course, noticed and appreciated. And people who are actively helping other students on Submiti will be given one extra credit point at the end of the semester. So ask your questions and let other people help you. Yeah, so let me scroll down through. Is the exam 5 gradable not showing up for anyone else? Probably because we are grading and there are still glitches on Submiti regarding the dates and how Submiti shows gradables. I would suspect that the fact that you don't see exam 5 is because we actually made it hidden so that you cannot or any student cannot look at the grading until it is done. Okay. So yeah, if you find that there are not enough cases in the PDF, well, cases, we only give you some of the cases, but the description should be pretty comprehensive. But if you don't find it comprehensive, if you have questions, please submit a forum. I think would be the best thing for that. But remember, yeah, you have to come in with a specific question, right? So and yep. Will the TAs be looking for on the homework for their what will the TAs be looking for in the homework for the manual component? So basically, code structure and following, some code code style. Okay, so the way you name your identifiers, your variables, your functions, and their amount of commenting, it should be sufficient but not overwhelming. So over commenting is as bad of a sin as no commenting at all. And just the overall structure, the way your code is broken into functions, that's that's one of the probably most important things. Do not make your functions huge. Those are known as God functions, and they're very hard to understand and maintain. So if you put your entire code, like 800 lines in a single function, that's not the best structure. I'm pretty certain. Those hidden cases are wrapping my brain. Well, come to office hours. We will try to help you. So, oh, quite a few of you lost power. Well, luckily I didn't lose power. So hopefully we're good. Hopefully I don't lose my internet connection either. So back to the homework. Yeah. quite often, and I'm looking at their submitted output for some of their students where they lose credit on hidden test cases, and in many cases it's not even the output that is incorrect. It's all I see is invalid memory reference. So there's something funny that you do with memory access or memory allocation that in certain cases, and those hidden cases are nothing really tricky. They are pretty boring. We are not trying to trick you or to come up with some esoteric corner cases. No, they're pretty common, pretty you know standard test cases. And the idea was actually that you come up with your own comprehensive set of test cases. And if you did, then you would it would be highly likely that you came up with test cases that are similar to our hidden test cases. Of course, if you write some code and then submit it, then look at their visible test cases and hack your code so that only visible test cases are satisfied, then of course you're not likely to get to get to get good points for the hidden test cases, because you're just hacking your code to satisfy what the test cases that you see. So instead, you should really kind of abstract from the submitted test cases and design your own test cases. Test them as thoroughly as you can. And some people have been doing that, and they've been asking on submitted, oh, all right, so I'm thinking about this test case. What would be the correct output? And then, of course, we are always willing to do help you and suggest what the proper expected output would be for a particular test case, even if it's not one of their visible test cases. So that's the right approach to this, right? Come up with your own test cases, know what you expect, what the expected output should be, and then code to that, code to the specification, not to the specific test cases that you see on submitting. So I know some students have submitted pretty much empty code just to see what their test cases are. You can full submitting and it will tell you what the visible test cases are, but I don't think that's the best approach. Office hours, you can always look at in our schedule. It's under course materials on submitting. And yeah, the lab is crazy. Well, yeah, that lab might be a little harder than the previous one or the one before, but our TAs and mentors are usually flexible, and for students who showed up at the very beginning of their lab period and worked diligently for the entire lab and still couldn't finish, they are usually offering some kind of workaround and some kind of extra extra provision to submit your work or to show them your work, maybe in office hours on Thursday or Friday, and get your checkpoints. So talk to your lab TA and mentors, and should be able to help you out with that. Yeah, over commenting is bad for sure. All right. Yeah, so big functions, even if there's one big function, it's still not very good. And of course, then the devil is in the details. It depends on what this function does, and but more likely than not, there is a way to restructure your code so that even this big function can be thought of as as a successive application of smaller tasks, smaller functions. Yeah, and it's not, someone's asking like, is a function of 200 lines a God function or no? You can tell by their number of lines alone. You have to look at their at what this function does, and whether it does one thing or several things or multiple things. Okay, so usually they're good. A rule of thumb is one function should do one thing, and that thing shouldn't be huge, right? So that thing shouldn't be like build the entire world in 7 days, right? So that that's the reference to that God function, right? So at the minimum, it would be one function per day, or maybe even one function per every action in within any given day, and avoid the other extreme. Avoid micromanaging. Avoid making functions very small, so that you have like a gazillion of functions, and it just becomes unmanageable. Yeah, someone says roughly 1.5 screens of code. Yeah, I think it's a good uh, empirical rule, but it's not really a hard rule. So, like I said, it depends. Okay, yeah, 500 lines definitely. If it's one function, it's definitely an overkill. All right, and I'm just yeah, checkpoint 3 actually ain't that bad. It's very short. If you know what you're doing, it's just a few lines of code. Okay, someone is still asking Comfort office hours. Yeah, questions like that. If you cannot find it yourself, but like I said, it's on submedia under course materials, then ask this question in the Q&A. So our panelists are getting bored. Remember, if our panelists are not getting enough questions, we will start, kind of winding down this incentive. Okay, just because we have typically 3, 4, sometimes 5 people sitting there and waiting to help someone. Okay. All right. So I think that's it with the initial questions. So let me start sharing something. Let me look at my agenda, and then we will get back to our slides. And I'm sharing something. Look at the chat, and I'll be keeping an eye on the Q&A. Yeah, someone asked me about the points for being panelist. I haven't updated it in like almost 3 weeks. I apologize. I have all the data. I just need to enter it on submittee. So please apologize me. I will really try to to catch up on this in over the weekend. Yeah, because it's Friday. Oh, almost forgot. TGIF. Yeah, it's Friday. So we are looking forward to hopefully a nicer weekend. Hopefully no rain. Any news on test 5? It's been graded. So as usual, we will try to get it done before our test 6, which is next Monday. But to be honest, I'm not exactly sure if we are able to make it. So we just finished grading homework 4, as you probably noticed. So homework 4 grades have been released, and we are, we as you probably know, we are a little struggling with grading. So grading homework 4 was particularly difficult because it's all manually graded. So homework 5 in that respect is going to be much better. But homework 4 was pretty rough, and that's why we are behind. And I don't think we're gonna catch up. But let's see. Sometimes our TAs and mentors do wonders, and maybe they will be able to finish test 5 before grading test 5 before test 6. That would be awesome. But yeah, and I will get Rainbow grades updated over the weekend. So it will include homework 4, which just got released, and their latest lab 6 is going to be there. And yeah, so if you think about it, all right, we only have 4 weeks left, exactly 4 weeks. So it's Friday today, and November 12th. So 4 weeks from now, December 10th, is going to be the last day of classes. So just one final stretch, just a little bit left. And Yeah, homework 6. So wanted to mention is already out. I have been out for a few days. It is due on Tuesday before the Thanksgiving break, November 23rd. And so, like I explained earlier, I don't think we would be able to move that deadline because we cannot have any deadlines on when there are no classes on during the break. And it's actually not that bad. It's not as bad as it may look. So and it's less parsing, but probably more thinking. Okay, and yeah, if you have any questions about homework for grading, then just file a grade inquiry. If you think you got no credit for something you deserve, by all means, file a grade inquiry on Submiti. And homework 4 is going to have average a lot lower than previous homeworks. It was lower, but not that terribly bad. So I think it was, I don't remember exactly, but I think it was high 70s. So which is less than our typical homework, which is like mid 80s, but still it's not like an average student was failing this homework. So I'd say it wasn't too bad. Okay, and in this, someone is saying in this class, not that bad means 10 hours of learning new material on your own so you can complete the assignment. Well, if you have any issues with that, it's best to talk to me. I don't think we have any material on the homework that was not covered, by the time the homework was due. So no, homework 4 will not be curved. So the average is high enough to not consider curving. Okay, yeah, and about the code structure, it's in the PDF. All right, so about God functions and structuring your code, it's in the PDF. All right, so project. So that's one of the few gradables that we are going to have in this class. So please form groups. So the gradable is already open for forming your groups of up to 4 people. And there is, so it's on Submiti. So if you go on Submiti, there's a team project. And if you click on create a team, you can create a new team, or you can do seek team partner. And some people are using this feature already. So if you don't know whom to work with, you can advertise your skills and find a team. So we will not be forming teams. So it's on you to join a team or to form your own team, however you want to do it. Please use all the resources available to you. So Submiti forum, Submiti team project feature that I just showed. Discord, office hours, just talk to other people in the class, and yeah, you need to find a group. Okay, and so the handout for the team project has also been posted. It's right here. So it's a kind of continuation of Lab 5 and Lab 6. And it's going to be due on the last day of classes, December 10th. But you need to form the group, the team earlier. So here are the deadlines. So a week from now, November 19th, you will need to finalize your groups on Submiti. So groups get logged after 11:59 p.m. on November 19th, next Friday. So, and there will be no changes to groups after that date. And of course, you can start working on your project even before you declare the group. But please make sure that you tell Submiti what your group is sometime before November 19th. So groups are up to 4 people, which means 1, 2, 3, or 4. I strongly discourage anyone from working alone unless you really know what you're doing and unless you're really good with C programming and you know all the material well and you have plenty of time. Okay, so this project is really meant to be done by 4 people to keep their load manageable. So if you do it alone, it's like 4 times the load. So strongly discourage against that. And all people on the team, they get the same grade. So try to get on a team with people who have decent skills. That would definitely help. And yeah, if you don't declare your group by November 19th, submittee will treat it as a group, as a single person group, which, like I said, is not a good idea. All right, what else? Yeah, so project has 2 parts. One is the code, and which is going to be auto graded and then manually graded for code structure and code style, like all our other coding homework assignments. And then the second part would be the write-up, project write-up. So it's going to be a PDF that you will need to submit. Okay, so it's not just the code, it's also the write-up. So please make sure you don't forget to submit it. The deadline is the same, but you do need to submit the write-up among other things. So here's the list of things that should be included in your write-up. Make sure that you explain in detail contributions of each group member, right? This is important because if someone did not contribute at all to the project, then that person is not gonna get the grade. Okay, so typically all group members are gonna get the same grade, but if someone did not participate, did not contribute enough, that person might get a 0. So that's why it's important to tell us exactly what part of how you work together and what part of work was done by each student. And so the deadlines, the deadline is December 10th, the last day of classes. Therefore, since it's the last day of the semester, unfortunately, we won't be able to offer you any late days. So even if you have late days left, you won't be able to apply them to this project because it's the last day of classes, and we need time to grade all those projects, right? Since there is no final exam in this course, basically the registrars will be expecting us to be done with this course by by Monday night, Tuesday maybe, given that Friday is the last day of classes. So it's going to be pretty difficult, and it's large class. So even if all groups are a size of 4, we are looking at 50 plus groups. It's a lot of grading. So that's why no late days, unfortunately, on project. My other alternative was to move the deadline 2 days earlier and say you can use late days, but I don't think that would be um, that would be fair or honest or even decent. So that's why the deadline is the last day of classes, but no late days. As for group project submission, I'm reading question, is it going to be like 1 people in the group submitted or everyone in their group? So it is sufficient for 1 person in the group to submit it. And we ask actually that only 1 person in the group submits, because otherwise if 2 people submit and their submissions are different, we don't know which one to take. So 1 person submits, but please make sure that whatever that person submits is something that the whole group agreed to. So I strongly encourage that you, once you form your group, which I recommend doing quickly as soon as possible, ideally today, and that once you form the group, you establish some kind of schedule to at least work together, and it doesn't have to be in person, it can be online, Webex, Discord, whatever, but meet at least twice a week and do some work together. Okay, that I think would help groups to to keep to keep this project on track and make sure you have that project done when it's time to submit. How many hours do you anticipate the project taking? I don't know. It's very hard for me to judge. It depends on the experience of people who are on the team. So if I had to guess, I would say 4 people, 30 hours. That would be my best estimate. But I can be way off. So you know, take it, take this estimate with a grain of salt. Big grain of salt. So it's just my wild guess. All right, what is TLDR? What we are doing for the project? It's Lab 6 on steroids. So you are going to take what you've developed for Lab 6, and by the way, you can use for the project, you can use the code written for Lab 5 or Lab 6 by any of their lab members. And then you add more to it to actually make it a processor. So Lab 6 we stopped at 32-bit ALU, and in the project you need to take it one step further and turn it into their processor. So it's similar to their data path diagrams that we have been looking at in the lectures. So and we will see more of them today. Okay, so basically you need to implement such a diagram as a simulator in your C code without with the restrictions like you cannot use if statements, right? Because we want it to be a simulator that kind of closely matches their circuit diagram with gates and you know components and controls and all that stuff. So like Lab 5, Lab 6. Will the difficulty length of exams and homework assignment be reduced while we are so expected to be working on the project? Yes. I will make every effort to ease the load on you. Can we cancel the rest of the homework assignments and tests? No. Fortunately, that's beyond what I think we can do. Will a Lab 6 solution be posted? Yes. Once all TAs report to me that they have no more people who are getting their checkpoints, we will release the solutions as usual. Is it like 30 hours of 4 people working? Yes. So yeah, if you want to multiply it, 120 man hours. I don't know. Again, like I said, it is my estimate. I could be very wrong with this. So start early. That's probably the most important part. Right, start early because everything that you need here, we either already discussed. So everything you need for the project, we either already discussed, or we will discuss today. And so you will have officially. We will have officially cover all the material that you need for the project today. And can we use Lab 6 solutions? Yes, I think I already mentioned that. Okay, and people are self-organizing themselves on Discord. That's excellent. He's underestimating. I don't know. I hope not. It's not. I think it's not that bad. But like someone already quoted me and was pretty angry that I said not too bad. So I probably better shut up and stop saying that. Okay. That's the project. All right, and test 6 next week. So coverage, obviously everything since their material that was on test 5. So roughly that's from their carry look ahead and carry look ahead unit, carry look ahead method of battling their ripple carry, and then memory, so all sequential circuits, and then let's see how far we get today and on Tuesday. So hopefully we cover enough of pipelining so that we can also added to test 6, but we shall see. All right, and yeah, from my notes from last lecture, so hopefully you looked at that file. So here it's just a very little, a small illustration of what shifting really is. All right, so it is just basically renumbering wires, renumbering bits inside the bus. This is towards our conversation of sign extending 16 bits to 32 bits, so the sign extend unit that appeared in some of our diagrams. Are we on week 11 on Zybooks? I believe so. All right, it's lecture 21, but we lost one lecture because of their was it their the Labor Day, if I remember correctly, right? So otherwise it would be lecture 22. So yes, it's the end of week 11. I'm looking through the slides and I still don't get what a data path means. Well, it's something that I can explain to you in office hours if you stop by, or you can look at their textbook, or if you noticed, I posted a bunch of materials that are available publicly to accompany our textbook, and one of them is, so there are like extra chapters and like extra material, and there's also a glossary. So there's this PDF, and I'm wondering if data path is here. I believe it should be. Data hazard is something we're going to talk about today, and data path is certainly here. So I know, please know and love your course materials under submittee. Okay, it has tons of useful stuff. And of course, it also should be in the slides, at least in their headings, right? Like, full data path is here. That it's actually the slide that we already talked about. There's one extra pop quiz that I wanted to offer you. So it kind of logically belongs to the previous lecture, more or less, but we will run it today. So it should be already open, and it's not really on the material that we talked today, that we will talk today, or we talk tomorrow. It's actually on the material that goes back like 10 lectures back or so. It's on what this instruction does, how it works, right? It's a MIPS instruction, so the question is really asking what this instruction does, right? So what does it load to S1? So their notation is, something, arrow means, moving or copying data. S1 is the register, M means memory, and in parentheses, it means memory at this address. All right, so the address is in the not in the parentheses, in the brackets, of course. So you need to basically decide, what is the correct expression that determines what gets loaded into S1. Okay, and with that, let's finally get back to where we left off. And I believe we talked about this main control unit. So now we need to pick up here our topics. All right. And so basically, one thing is, one of the things that will probably take most of your time when working on your project. And, if we ask you to write, to draw a data path, their components should be pretty easy to draw, but then coming up with all the control signals is a little more time consuming. So ALU control is their control bus, the control signals that are going to be used to control their ALU, and this is something that we talked about in the previous slides here. So we have this ALU control that is used to determine the function that we want our ALU to perform. And so, we circle back to our test 5, where last question was exactly to design an ALU that performs a certain set of functions. And here we assume that ALU OP, this control signal, is derived from the opcode. Remember, opcode, it is the code of the instruction. So basically, we are saying that ALU op is directly derived from their code of the instruction. And here, this table shows exactly how this is done with additional pieces that we call function, which, as you remember, hopefully from our previous conversations and from our MIPS reference card, is just another part of the instruction. So let me just point you to our beloved reference data reference card, and you see that this is MIPS function, right? So these 5 bits is a MIPS function, and if you look at their formats, right, you see that here is this part of the instruction, right? So it's bits 0 to 5. It's funct. We also know that there is a shamped, a shift amount that is only, so this field is only used for shift instructions. So this is all very relevant to your project, to what you're gonna need to do in the project. All right, and so this control signals for ALU will be just generated by some combinational logic. So it's not a sequential circuit; it's just combinational logic, as we can see, from this slide, and as we understand, right? Because it just some transformation of the codes derived from the instruction, from opcode and funct, and potentially other fields, and therefore we can just hide the complexity of those of that combinational circuit by just representing it as a black box, which we call ALU control, or just control, so we can combine it with the rest of the circuits that generate control signals, and just call it control, like here. So this diagram we already talked about before. So to implement those other controls not related to ALU operation, we first need to understand where the inputs for those control signals are coming from. And the vast majority of inputs would be coming from the instructions, right? So from the code of the instructions, like opcode, funct, and all those register names or register numbers, and so forth. There are a few exceptions, and we will talk about them. Were the slides updated? Yes. So I actually added a few slides that would help you with the project, and the project PDF has actually references to those new slides. Yep. All right. I think this is the beginning of the slides, of their set of slides that I added, and that you should find helpful for the project implementation. So remember, those control signals. So register DST is one of them, and so we had this diagram. Not even this. It's not even on this diagram, but we will see it on our on the diagram further on. So let's talk about those control signals, and then we will see them on the diagram. So register DST. DST stands for destination. Yeah, mysterious control line. But let's discover all the mysteries of those control lines. This control signal is a selector for a multiplexer, which decides which field in certain R format or I format instructions are written to. Okay, so why do we need it? What is it all about? So if you think about our R format instructions, right? That's the R format right here. Okay, so this is the destination, right? Always, so destination, and it's very nice and neat that we have 3 registers. 2 are source registers, RS and RT, and the third one is their destination register. And of course, in their instruction, mnemonic, the way we write it, the destination register is the first one that we mentioned, right? Remember, it's like add, and then the first register that we put here is our destination register, right? So that we refer to RD. So in the instruction format, the order of registers is different than in the mnemonic, but it doesn't really matter. It's just a level of translation, so it's perfectly fine. So this R format instruction is very nice and neat and organized. That it's always 3 registers, and one of them is always the destination. So it makes it easy to write to our register file when we need to update the register. And unfortunately, there is another format that we know as I format instruction, where there are only 2 registers. We call them, source registers. One source register 2, RS, RT. And if you think about load word instruction, something like T0, 0, T1. Okay, something like that. So we don't write to. So we write to this register, right? So we read from this register, then we compute their effective address, and then we write to this. Sorry, I got myself confused with SW. So we yeah. So all right. So let me get it straightened out. I believe this is typo, right? It should be LW, right? Because LW, we are loading the word from memory into our register, right? So that's load W, and it needs to write to the register, right? Whereas if we have SW, so we are taking the value of T0, and then we are writing it to memory. We are storing into memory, given this address, right? So here we're just reading 2 registers. From this, you can see that, with I format instructions, we have a case where we need to write to one of the registers, one of the 2 registers, and that means that so that register would be one of those. It would be RT. So in fact, we need to write to RT. And that kind of makes things complicated across the board if we look at all the possible instructions that we need to implement, because we no longer can say, well, we always write to RD, right? Because for some instructions, we have to write to RT. And that's why we need this control signal register DST that would decide whether we are writing to RT or to RD, right? Because our format instruction also has RT. So we have to make sure that for our format instructions, we are writing to RD. And for certain I format instructions, we are writing to RT. And that's why we need a multiplexer that selects that, and their register destination control signal to serve as a selector. Okay, so register destination should be, and obviously now we have to come up with just a particular method of encoding. So if the selector is 0, we say that their value will be written to RT, and when this selector reg DST is 1, value is going to be written into RD. So obviously, how do we produce this control signal? Reg DST is a function of the opcode field. So if instruction is LW, then register DST should be 0. So that confirms, my suspicion that, of course, this was a typo. All right, and for all other instructions, obviously, reg DST is 1, right? Because load word is the only exception. All right, so next, reg write control signal. This is used to, to initiate a write operation to the register file. So when the reg write is 1, is active, we say that it's a write to the register. So whatever register is specified in the write register, that register is written with the data on the write data input. So obviously, reg write should be 1 for all our arithmetic logical instructions, all our R format instructions, because all those instructions write the result back into the register. Also, it should be 1 for load, because as we just discussed, load does write to the register. It's not register D, it's register TRT, but it's still a write into the register. So for other instructions, it should be 0. And remember, we are working with this short list of instructions with a smaller set. So all other instructions in the smaller set are just store and branching. So for them, obviously, we don't need to write anything to the register, and that's why this reg write control should be 0. ALU source control. So that's our next control signal, and it is used for their as a selector for a multiplexer that selects the second operand of our ALU. Why do we need 2 operands? Well, because we might be adding data read from the register file as our second operand, or we might be adding their immediate value that comes from the instruction. So that immediate value needs to be sign extended, so as we discussed before, but those are 2 choices, and we have a multiplexer to control this. Okay, so what are the values of ALU source? Obviously, it's 1 when we need load and store, because in this mode, the data that we read from the second register, right? So read data 2 is used as their base address, and then we add their offset to that. So that's why we need that. And so for all other instructions, ALU source is just 0. All right, moving on. Memory control. So 1 tells that the memory needs to be read. So basically, it's a read from memory control signal. So obviously, when do we read from memory? When we are performing load, because we are loading from memory. So we are reading the map. We are reading from memory, and 0 for all other instructions. Memrite, that one is easy. You get it almost, almost free. So it's kind of opposite to, well, it's complement, I should say, to mem read. So it's 1 when we want to write to our memory, and that means it's 1 for store and 0 for all other instructions. Mem to reg, memory to register. This is a selector. This control signal is used as a selector for the multiplexer that decides which value is going to be stored in their register file. So there are 2 options. If mem to reg is 1, it means that the selected value is coming from memory data output. And so we are writing to the register the value from memory, the value that was read from memory. And obviously, this one is for all our load arithmetic logical operations. All right, so load is an example where the value is coming from memory. And 0 means that the selected value is coming from the ALU output, so it's all other instructions. Next, PC source. This one I think we already talked about. This is a selector for the multiplexer that decides what their next value of PC is going to be. So it is either 0, in which case the next value of PC is going to be PC plus 4 from their corresponding adder, or it is 1, which means that we are taking the branch and we have their branch address computed. So their possible values are obviously 0 and 1. 1 is for BQ if registers are equal. So this is important because there is this if. right? And if registers are equal is not something that you can derive from the instruction code or any part of the instruction itself. So this one is a little bit more complicated, right? Because there are two conditions. BQ, you know whether an instruction is BQ or not from the opcode, from the instruction, but whether registers are equal or not, that you don't know from the instruction. So you have to actually you actually have to factor in the zero output of their ALU. And if you think about it, that zero flag, that zero signal is the same as their EQ or equals signal that we asked you to design as part of your 4-bit ALU on their on the previous test, on their most recent test. So it's 1 for BQ and obviously 0 for other instructions. Or if it's BQ but registers are different, then this PC source control signal should also be 0. All right, so that's something that we just talked about. PC source depends on the result of the ALU operation. So we need to and their BQ, their signal that indicates whether the instruction is BQ or not, and ALU 0 output. And we have seen there's this little AND gate that generates this control signal. Okay, it's just an AND between their BQ bit and their 0 bit. And if the output is 1, it means we are taking their branch, and it means that the PC source has to select the corresponding value to be loaded into the PC, and that corresponding value would be their address to which we are jumping, which is relative. It's PC plus their displacement that is coming from the immediate value of the instruction. All right, so yeah, we call this branch. The output of that AND gate, we called it branch. All right, so yeah, someone's saying it's so fast. Well, it's a lot of ground that we have to cover. But if you follow my advice about dealing with the elephant and just do one little bite at a time, one little piece at a time, I think it's manageable. So for all control signals, remember they are binary, so they're true or false, so you can turn it on and off. So essentially they are like flags that indicate a certain behavior. So most of those control signals derive their outputs from their instruction themselves. All right, so that makes things hopefully a little easier. So figure 418 in our computer organization and design, COD, I think that's actually your best friend. After of course all our TAs, mentors, and myself, I think your textbook is your next best friend. All right, and if you look at by the way, yeah, so I was hoping to go through one of those animated figures, but I don't think we have time. But they are different from their static figures in the textbook, because here they actually show some specific values. As example, they use color coding, so you see, what gets from what, right? So for example, you see that this 488 is the value read from register 7, right? So 00111 is register 7, okay? And you see that the green address is the address of register 2, and read data 2 is the output that gives us the value from that register. Okay, so that I think is a lot more interactive than static uh, pictures, just snapshots in our slides or in our textbook. And they also comment on their values of the corresponding control signals that that are relevant to a particular component or a particular operation. Like here it's the operation, it's the it's part of the execution of the instruction where we read values from the register file. All right. So if you're using Zybooks, please make use of those animated figures. I think they are very nice and very helpful. But we unfortunately have to scroll down, and I'm looking at, yeah, it's probably in this section about all the control signals. So if I strongly recommend that you read at least this section from chapter 4. So in the textbook it's chapter 4, in Zybooks it's kind of chapter 10, but it's of course the same text, the same material. So it's what we just covered about all the control signals, right? So starting from designing their ALU control, okay, and showing which bits are coming from which parts of the instruction. Remember, this is the opcode, this is the the funct. Yeah, I think I misspoke earlier. I said it's 5 bits. No, it's 6 bits, 0 to 5, so it's 6 bits in total. Okay, and so this is the table that we saw on our slides, and this one as well, and then moving forward. So this is a summary of our control signals that we went through in the slides that I just added. Okay, so they describe what each of those control signals does. And remember their terminology: deasserted means 0, asserted means 1. And so then there is this, complete data path diagram with control unit, and it's called simple, just to make you feel miserable. No, I'm kidding. It's simple because it's not pipeline. That's what they mean by simple, right? So what's coming up is a little complication when we want to get to squeeze more performance out of our processor, and we switch to a pipelined design. So that's why they call this simple, because it's not pipelined. All right. Yeah, but please don't let this terminology upset you or discourage you, right? So I agree with those of you who would say, yeah, it's not exactly very simple, right? So this is the ALU control, right, that we talked about, okay, that we could have included in this blue control with the other controls, but we could also make it like a separate separate component if you want, just to make it easier to analyze this diagram and make it separate, make it clear that this ALU control unit produces, or component produces, all the control signals from for the ALU. All right, and then finally, I think this is one of the most useful tables here. Okay, so this shows for different types of instructions what control signals we need for each of those instructions. So our format is, remember, your add, and XOR, things like that. And this is the set, this is how you need to set control signals for those instructions. All right, for load word, for example, you say, oh, okay, for load word, we need reg DST at 0, whereas for our format instructions, it has to be at 1. And like you can go line by line, row by row, and just compare. Like, for example, you take branch and you see, oh yeah, branch is only relevant to BEQ instruction, so we want branch to be 1 if BEQ instruction is currently executing and the registers have the same values, right? So if there is a 0 flag at the output of the ALU. Okay, so if there's an X, it just means don't care. it means you can set it to 0 or 1, it doesn't matter. And then if you look at each column, it kind of gives you an idea of how to design those control signals. For example, for branch, you know, okay, the only time it's 1 is when there's BQ and registers have the same value. Okay, so it's, you can, you know, look at it at a very simple truth table, and you can based on this, you can do something similar to K-map K-map minimization, and come up with their expression that would tell you how to generate each of those control signals. And this is something that you need uh, uh, to implement in your project. And if you think about it, it really comes directly from here, okay, from this table. So there's a lot of useful data in this table. Okay, and yeah. So, and this is our data path, and now we need to look at how each of their type, if each of instruction types are executed given our data path, given our processor diagram that we built. So let's see if there's anything else. All right, so that's their whole thing. Okay. I don't think we have added anything new. We basically only separated ALU control from the rest of the control, and we explicitly labeled all the control signals that appear in the slides above that I just added. So everything else should be familiar to you, but if not, please ask questions. So this is probably one of the most complicated of those simple diagrams, and we need to make sure that you understand every single wire, every single control signal, every single component here. Okay, because it is something that is extremely highly likely to appear on the test in one form or the other, because this is really important stuff. Not just because I'm cruel and crazy and as some students say, sadistic. No, I don't think I'm any of that. But of course, some students might disagree. Hope not. Anyhow, so I think this is a very important diagram, because it really shows what the processor is. And if you understand how it functions, if you can sort of see how this static diagram becomes live, and you almost see there all those bits, zeros and ones, going through all those wires, propagating according to the arrows, and how this whole machine really works and allows your instructions to be executed, right? So performs the result, be that addition or jumping to another instruction, or storing something in the external memory. So this is really important to understand this diagram. And on their test, some questions might be, we might give you this data path with control diagram, but mess it around a little bit. Maybe add a component somewhere that doesn't belong here, or maybe erase one of the wires or rewire one of the wires to make this broken. And then we may ask you to find what exactly is broken. Okay, so that is a good test of your understanding of any circuit, any diagram, is to make malicious changes and see if you can spot them. Or another direction, another type of questions might be, we show you this diagram the way it is supposed to be, right, with no errors introduced, and then we describe some kind of bug, right? We describe you some behavior which is abnormal, and then we ask you to identify what is the likely cause of this, right? So for example, we might say, well, you execute their instruction, which is a branch instruction, but their program jumps to their to the target address with an error of four 4 words, or one instruction, or something like that. Okay, and you would need to identify the unit that is likely to be responsible for this error, right? The unit that becomes faulty. And of course, it would be like, oh, if we replace this unit, then it's going to fix this problem. Okay. Of course, in real life, you cannot just, take out shift left 2, faulty shift left 2, and replace it with a new shift left 2, right? Because it's all inside an integrated circuit. But from their understanding of their conceptual design, this kind of thinking is very important. Like, what component is responsible for what behavior, and if the behavior is wrong, being able to identify which component or components are responsible for that. All right. So it's just a heads up if you're thinking, how to start preparing for the test. That's definitely one of the, one of the directions. All right, so now let's look at how different types of instructions go through this, data path, execute and produce the desired result. So in those slides, so there's a series of slides, and the slides are just figures from the textbook and books. So it's it's nothing really different. So their convention is their grayed out parts are not used for a particular instruction. So starting with our data path with control, which is our for the time being is our final simple diagram, right? We want to see how which parts of it are used for which instructions. So R type instructions, you can think of your add, for example. So which components are not used in the execution of the add instruction? So obviously it's not branching, so we don't need this whole part which computes the target address for the branch, right? So this whole part is not used. That said, so when I say not used, how should you treat my words? You should understand that shift left 2 and our adder, they are hardware components, and you cannot just turn them off individually in the vast majority of cases. Okay, at least that's not the level of abstraction that we are considering. So all the components work all the time. So when we say unused, it means that whatever their result is, we're not going to use it. In this particular case, why? Well, because we know that it's not a branch instruction, so this control signal is going to be 0, which means that this output of AND is going to be 0, and that means that it doesn't matter what this shifter with the adder produced, this result is not going to be used for this instruction. This result is still going to be fed to the multiplexer. It's just not going to be used for this instruction. It's never going to be routed to the output because the multiplexer is always going to be in this state, right? So that's the meaning of unused. It's still going to be generated, right? The work will still be done by the corresponding hardware. You cannot just comment out hardware. It's not that simple. Will the multiplexer will simply stop the signal? Let me move my windows of the red parts. Yeah, so for the R-type instruction, the multiplexer is never going to route the lower input to the output. It is guaranteed, as I showed you just now. Okay, so in that sense, it doesn't matter what this adder computes, right? Because this value is not going to be used in this mode in for R-type instructions. Right, and similarly, if you look at other grayed out components, oops, right, we have memory. Why is it grayed out? Because we know R-type instructions do not work with memory. They only operate on values that are read from the register file. So registers are not grayed out, okay, but data memory is because it's not used. And again, treat they're not used as in the sense that I just described, right? Not literally, but kind of more of a, from their usage point of view. And this sign extend is not used, right? Because you know that it is only relevant for immediate instructions, right? So I-type instructions, because you see that it is using this field that we for immediate type I-type instructions called IMM, immediate. Those 16 bits. So this understanding of which hardware components are relevant or irrelevant to the execution of a particular type of instructions will actually help you answer questions about, something is broken, right? So if we tell you something is broken and it's an add instruction, this broken, whatever it is, cannot be in data memory or cannot be in the sign extent module, right? Or cannot be in their, shift left to module, right? Because those are not effectively used for this instruction. And in our Zybooks, so here is again, I just love those diagrams because they have real values here that travel along their wires. So it's an animation that really you can think about this process as something live, as a living thing, and you can look at it in the dynamics of it, right? So let's start, and we see first that we need to read their instruction. So the instruction is read from the instruction memory. So hopefully it's not too fast and you were able to, to see how this 32-bit word of instruction was read from our instruction memory. And now it is shown to us, and you can actually look at all the codes and tell me what instruction that was, or that is, which instruction it is. Okay, just based off those codes. Yes, it is Ed. Thank you. Excellent. Okay, and now, so these 32 bits are here, and all the other stuff, so all those wires that go off from here are referring to instruction 3126, instruction 21, 25, 21, and so forth. They all refer to this instruction word, right? So see 0, 5, 10, 6, so all the fields of the instruction. So you see what gets fed to where. So the register file, for example, gets instruction 2521. It's this, right? So this is source register 1. This instruction 2016, 20 to 16, bits 20 to 16 is source register 2 to read, and so forth. Okay, and next step, you see how, yeah, this is broken down, and you see we read two registers. Here their values are. This is their opcode, and this control black box, which we mentioned before, is their combinational circuit, which you will be designing as part of your project, right? So with their input of all zeros for the opcode, their registered destination is 1, okay? And that switches this multiplexer to their lower input. So that would be their right register. 15 to 11, and we know, okay, this is our RD. So in this mode, RD register is going to be written as it should be for the addition. So next step, step number 3. We generated more control signals, all right? So for branch 0, for memory 0, because we don't need to read memory. So all those values, remember our table that I said is a very important table. So that table gives values for all those control signals for each type of the instruction. This is an R-type instruction, so basically we just take the values from the table. And then next step. This here we. So what happened here? Did I miss it? So step number 4. We are supposed to compute their value of to compute their sum using their ALU. So from 50 I can't really see it. 55 or 56 and 33. Okay, so that I think is what was supposed to happen at this step. And then next step, right? Mem write is 0 because there we don't need to write to memory. So note how our other control signals are properly computed. So ALU operation is 1, 0. Mem write is 0. We're not writing to memory. ALU source is 0, and reg write is 1 because we are writing to the register. Okay. Someone says, yeah, it's a very good observation. Someone says, pretty much this diagram is our final project. Exactly. That's a very relevant observation. You just have to do it not with a diagram, but as a simulation in your C code. Okay, someone says it doesn't look too bad. Well, at least I'm not the only one who says that. It kind of makes me feel not as bad. Yeah, hopefully don't regret it, as I sometimes do when students take those words back to me and say, well, it wasn't at all not that bad. All right. Anyway, so that's step 6, right? So we are writing back to the register, right? So it was 55 and 33 because we see that the sum is 88, which is written back to the register, and that's it. That completes our instruction execution. So one extremely important observation about this diagram, step by step. Why it is important to see it step by step? Because this is something we're gonna start talking very soon. You see the stages of program execution. So this is we fetch instruction from memory, right? So this is basically stage or phase number 1, which we are going to call instruction fetch. Then there's going to be the next couple of steps is we are taking their instruction code and we are producing all their different control signals. So this is called decoding instruction because we are analyzing the bits of the instruction and corresponding corresponding combinational circuits produce all necessary control signals for the next stage, for stage number 3. So this stage number 2, is called instruction decode, or ID. The first stage was IF, instruction fetch. The third stage is called instruction execution, or EXE, execution. That's when their action prescribed by the instruction is executed. This is when our ALU computes the result. Okay, so it's this step number 4, when our ALU, and I don't know why it is not shown yet here, but that's when ALU computes the result. And then we have 2 more stages potentially. One is to write to memory, and the last one is to write to the register file. Obviously, as you can see, the memory write happens first. Of course, memory write is not necessary, is not needed for all instructions. In our case, memory write is not necessary. It's not that kind of instruction. R-type does not write to memory, but there will be other instructions that will use that phase, that stage. So stage number 4 is memory, MEM. So, and then the 5th stage is what we saw here for this instruction, is when we write back to the register file, and this is called write back stage, WB. Okay, and so that's why it's important, to see the dynamics of this, right? Because it corresponds to the stages of instruction execution. So we can see there are 5 stages in generally. So not all stages are used for all instructions, but in general there are 5 stages. All right, so we are done with R-type instruction, and Zybooks have those animated diagrams for all other types of instructions. We don't have time to go through them in that much detail, but if you're using Zybooks, of course you can play with it as as long as you would like. We just going to proceed with our static slides. So load instruction, obviously it's not a branch, so this piece is not used. And on in contrast to the R-type instructions, memory is used, right? Because we are loading from memory, and that's why, yeah, it's not grayed out, as you can see. And since it's a load instruction, it has this offset, which is encoded in the immediate field. So this immediate field instruction bits from 0 to 15 are used. So it's 16 bits, they're sign extended, and then they travel here, right? So it means that our ALU source should be 1, right? Because we want this to happen, right? Because we want to compute the effective address that is then going to be used to go to our memory bank, right? So this is a register, right? So read register 1. So this is base register. So for example, if we have load W T0 0 T1, well, let's make it not 0 but 10. So this is going to be 10, right? And I assume, of course, hexadecimal 10. Right, so then this is going to be sign extended, right? In our case, it's a positive, so it's still going to be 10. Okay, and then the value from T0 is going to be read. So let's say that value is 10,004 four zeros. So we're going to have 10, 4 zeros. Okay, so this is what we call base address, right? Like, if we are accessing an array or something, and this is their offset, right? So we are adding offset with a base address, and the result is the address in memory where we want to read our data, right? So there, this here is going to be 1004, and then 0, 0, and 10. Okay. So that's that. And then the value read from the memory is written back to the register file. So this read data is the value read from the memory, which means that whatever we are writing back to the register is coming not from here, but from here, from our read data output of data memory. Okay, because previously, remember, for the R-type instructions, we had this, we were using this wire so that we could route the result of ALU, like the result of our addition. We would use this wire like that. Let me use a different color to make sure that we are all on the same page, that I'm referring to the previous instruction, right? So for add, we would take the result of addition in our ALU and route it back as their value to write back to our destination register. Okay, but here for the load instruction, it's different, right? We are writing not the result of their ALU, because that's just their effective address of the memory. It's not the value that we want to be stored in our register file. We want to store the value read from that from memory from that address. So you see how this is a level of indirection. Okay, so the value in the register here is not the value that we want to write to T0. It's the address, it's the base address, right? But in any case, it's the address that is referring to the memory. So this is like a pointer, right? So if you think about it, it's like doing something like this, right? We want to read the value that is contained in the variable which is an address, right? So T1 is that variable that contains the address. So we want to read not the address, but to actually dereference this address, right? Take this address to the memory bank and read what's in that, at that address in the memory bank, and then take it and load it, write it into to 0. So you see the correspondence, right, between their indirection using pointers and how it is reflected in our MIPS ISA. Okay, and I'm just scrolling through their through the chat, and all right. So that was load, and next is branch unequal instruction. Okay, so obviously here we are going to be using this part, right? Because this is what computes their target address to which we want to jump. Oh, and by the way, yeah, on the previous slide, it means that this mem to reg is at 1, right? So we see that clearly for this instruction, it's got to be 1, right? We want this input number 1. Yeah, I think it's just shown upside down, so that it can be drawn easy, but it is labeled. So see those zeros and ones here. And by the way, labeling is extremely important. Okay, so please, any diagrams. I don't know if we're going to have more diagrams. Well, we're going to have at least some diagrams still coming up in exams, but maybe not as many as before. But anyhow, make sure you label everything, right? Make sure you make it easy for us to read your diagrams. All right, so back to branch. So obviously this is this is their hardware that computes their target address, right? By taking their current value of PC, and it's already incremented, so it's PC plus 4, but it doesn't really matter that much. And then taken from the immediate field, you see how it is from here, right? From the instruction, and then sign extended, but then the journey of this field is not over. It's shift lefted to, because we want to make sure that the address that we are adding is aligned to the word boundary. Okay, so that's why we shift left 2, and then we add, and this is the new value for PC. So we need to make sure that this multiplexer is like that if the branch is taken, right? So branch is taken, because if branch is not taken, of course, it's going to be different. It's going to be connecting this top input to the output, right? So if the branch is taken, this signal is 1. We know it is branch, and 0 from the ALU. All right, and yeah, data memory is not used. We are not writing or reading anything from data memory. And note how these pieces are grayed out as well, because we are not writing back to the register file. So because there's nothing to write, right? If we took the branch, if we have taken the branch, we just left, and that's it. That's the only action. Nothing to write back, but just by their meaning of their of this BEQ instruction. When you branch, you only care about PC. Well, you also care about the values that you read from the registers, right? So read data 1, read data 2, right? You want to compare them, which means you have to subtract them, which is done by the ALU. So that's why you want this multiplexer to connect read data 2 to the second input of the ALU. So this is your ALU source, which in this case you want to be 0, okay? So that it is connecting like that, all right? So, and then you are programming your ALU to perform subtraction, right? So this is effectively subtraction. So that this is the ALU control. Note how this is not a single wire. See how thick it is, which means it's a bus of some number of wires. Okay, whereas mem to reg, mem read, you see those are thin lines, which means they are just individual signals, just one, just single wires. So when you're reading the diagram, please pay attention to this. It helps you understand what is going on. So after we subtract, 0 means the values of those two registers is the values are the same. All right, and if 0 is 1, so this is a little crazy, right? If two values are the same, their subtraction result is 0, but the 0 flag would be 1. So the 0, this 0 is really is result 0. It's kind of question, and if you answer yes, it means true or 1, right? So if result yes, this 0 flag is going to be 1, okay, not 0. And if it's a branch instruction, and if the branch is taken, so their values read from the registers are the same, then it's 1, and yeah, then the only other thing that matters is the PC, right? Because then we just take their immediate value, which is their offset, we add it to the current PC plus 4, and that's it. Next instruction is going to be fetched from their new address. It's quite natural. There's nothing else we need to do. We just load the new address into PC here, and on our next clock, that instruction will be used as the address in our instruction memory, right? Instruction memory conceptually is the same as data memory, except for our program cannot write to it. So, for our program, it's a read-only memory. Of course, to put that program into that memory, we have to write to it at least once, but it can be done, so programs typically do not have write access. Well, sometimes they do, but let's not overcomplicate things and just assume that you have to, basically flash your instruction memory with a new firmware, which is your program, and then the instruction, and then that program cannot change itself, cannot overwrite instruction memory itself. All right, then, well, we are actually almost done. So just a few things to talk about. Jumps, right? That's the last thing that we need to talk about. It's extremely simple. So jump is unconditional jump, so nothing to compare. So this is really just, take your PC and replace their least significant 26 bits of the PC with the address that is coming from their instruction, right? So note how they, of course, their designers of MIPS wanted to have the address field as large as possible. So they even came up with their opcode, which well, opcode is still five bits, right? So no, in this architecture, they decided to have all the instructions have the opcode of the same length, so it's the same 5 bits as all other instructions. So never mind, yeah, but there are no other fields other than the opcode, right? So this is opcode and their jump destination. What needs to be done to execute this instruction? So we take these 26 bits from the instruction, and we assume that their address to which we are jumping is word aligned, which means we need to shift left by 2, and then we still miss 4 bits, right? Because it's 26 and shift by 2, that's kind of 28 bits that we can compute, but we need to have 32 bits. So, right, so this is 26, this is 2, and we still need 4 more bits, right? All in all, it should sum up to, to 32. Okay, so we need to take their address from the instruction, shift left 2, and then use those 28 bits to replace the least significant 20 bits of their PC. That's all there needs to be done. Do we need to have do we need to extend the address to have length 32? Yeah, I think I just explained how this is done. So, these 20, let me change the color. These 28, we just discussed how we obtain them from their instruction itself. And these 4 are old PC. So their 4 most significant bits of their program counter are not changed as the result of the jump instruction. So what it means is if this is your entire memory space, right, from 0 to F, 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 F. All right, I should have 8 Fs, right? And you are somewhere in the middle, like here. Okay, here's your instruction. It means that depending on where this instruction is, it may not be able to jump to any to any position, to any address in the instruction memory. This is instruction memory, IM. Okay, so for example, if we are here, we clearly won't be able to jump all the way up to here, right? Just because this jump would be more than 2 to the 29th minus 1 words away, okay, and bytes away. Bytes, memory is byte addressable, so it's in bytes, okay. Whereas our full memory is 2 to the 32 bytes, okay, from 0 to 2 times 2 to the power of 32 minus 1. So in total, 2 to the 32 bytes of memory. So it means that this jump is limited, right? The range of the jump is limited. It is not the full range of all addressable memory, right? But this is not, this is a little of a limitation, but not too bad, right? Because programs are rarely as large as, you know, uh, requiring jumping very, very far. And even if you encounter such a case, a compiler can easily work around it. So, for example, it can jump to somewhere within its reach, and then it may put an instruction here, which is another jump, and it can jump to here. So with an additional jump, you can jump to any location in the addressable memory. So it's a minor inconvenience, right? It's a compromise. All right, and so that's how this data path with jumps looks like. So we take their 0 to 25 from instruction. This is our address. We shift left 2, and then we just take their 4 bits from their PC and combine with the 28 bits. Note how this says 24, right? This is going to be 4 into a single bus. So this connection here, it just means that we are combining 2 buses, right? So one bus that has 28 wires, and then the other bus that has 4 wires. We're just combining them into a single bus that has now 32 wires, and that's it. And then this bus keeps traveling. So one thing that you probably noticed is that here, this multiplexer, it's a 2-input multiplexer, but it is capable of switching buses, not individual bits. So it's a little modification of our 2-input multiplexer that we have seen and that we have played with, because that one could only switch a single bits. So each input was a single wire, single bit. Here, this one can switch 32 bits at a time, a 32 wire bus at a time. So basically, you just need 32 2-input multiplexers that are connected in parallel, that have the same selector signal, so that they work synchronously. They all 32 switch either to first input or the second input. So the design of this would be very easy. Okay, and so yeah, this adder, this adder still adds, PC plus 4, no matter whether we need it or not, whether we branch or not. It still does this job. Of course, we still need to, have our PC engaged and our instruction memory for the jump instruction, but we are not using anything else. So everything else is grayed out, saying that it's not used in this mode. It's not used for an unconditional jump instruction. All right, so we are actually done with their data path, and for their what they call a simple case, right? So non-pipelined, and we can look into what we've done and think about the performance. So we see that different instructions clearly take different time to execute. So for example, which would be the fastest instruction to execute? What do you think? Jump, exactly, because it does very little job. So all it does is the shift left, and then it is ready to load this value immediately back into the PC. So obviously this is very, very quick. What do you think would be their longest, the slowest instruction, the instruction that would take the longest? It would actually be their LW, right? Because it reads the reg. So for LW, think or store W, doesn't matter. It goes to memory, exactly. So we fetch the instruction, we read the register file. So we decode the instruction and we read the register file. We perform ALU computation. And note, this is all sequential, right? This has to happen in order, you see, because all the connections are sequential. So we first do this, and before our register file gives us the read data one, our ALU would not produce the correct result. And before our ALU produces the correct result, we cannot read data from memory. And until we read data from memory, we cannot write it back to the register, right? See how this is all this is sequential. And this is going to be the longest chain. Read the instruction memory, decode and read the decode instruction and read the register file, perform ALU operation, access memory, and then write back to the register file. So it's a lot of things, and even R-type instructions are faster because see how here we bypass memory, so we can do it a little faster because we don't have to deal with memory. So clearly, load instruction is the slowest, the longest instruction, the instruction that takes the most of the time. So indeed, critical path is the load instruction. So previously we discussed that we really want all instructions to have the same, to have the same clock. We obviously want to have a single clock for all instructions. It simplifies the design tremendously. And that means that we have to kind of select their clock period based on their slowest instruction, their load instruction. So we say it's on the critical path, and that critical path, if I asked you to show that critical path, you would show, exactly what I just showed you. This sequence of a data, this sequence of components that have to be engaged, that have to do some work in order to perform this instruction, like instruction memory reads instruction, then register file reads the registers, and one the next little step cannot be done before the previous step is done. That's why it's called the critical path, right? It's sequential, and we cannot we cannot do anything about it. We cannot optimize here. So and this is the path, right? So this is what they call the critical path: instruction memory, then register file, then ALU, then data memory, and then register file to write, right? So and obviously we don't want different clocks for different instructions, which means we have to, kind of account for the worst case. And this is very unfortunate because it means that other instructions, while potentially able to execute much faster, will only execute, in the same amount of time as the load instruction. Okay, and of course it hurts the performance. So what do we do? Oh, you're gonna love it. We're gonna pipeline. So we're gonna perform pipelining, and we still have 6 minutes to for a brief pipelining analogy. So this is one other principle that I subscribe to for sure, is trying to come up with some real world, common life analogies that help us understand difficult pieces about computer engineering, computer hardware, or electrical engineering, anything concepts, any of those concepts that are more that are harder to kind of visualize. So here's our pipelined laundry analogy from their textbook, and actually Zybooks have this animated. So if with your permission, I just gonna switch to their animated version of this figure, just because I like it. All right, so and what do we start with? Well, we start with this, which is a diagram that represents doing your laundry. So here we have certain hardware. So this is the washer, the blue thing. This is the dryer, the white thing. This is the folding table. I don't know, it doesn't look much like a table, but it looks like a stack of folded clothing. So it is just the table which you use to fold your clothes, and this is the closet where you keep all your clean laundry. Okay, this is the closet. So those are 4 hardware resources, and obviously, if you need to do your laundry, you just do it sequentially. You wash, then you move your stuff from the washer to the dryer. Then you wait, however long it takes to dry, and then you start folding. Once you're done folding, you move the entire stack to their closet. And then if you have a second load of laundry, you just repeat this process. So if there are 4 different people, A, B, C, D, you can come up with whatever names for those folks, right? Then we only have one washer, one dryer, one table, one closet. Then we cannot share them, so we have to do those loads of laundry sequentially. And that means that if we have 4 people and each stage is half an hour, 30 minutes, as you can see from this timing diagram. So on top of here, it's time. So if we started at 6 p.m., when are we gonna done? When are we gonna be done with laundries for all 4 people? Well, only at 2 a.m. And if you look at why this is obviously not the most efficient way, you look at each individual hardware resource. Like look at the washer. For what time was our washer used? Between 6 a.m. and 6 p.m. and 2 a.m. in total. So in 8 hours, right, from 6 to 2, it's 8 hours. How many hours was our washer actually used to wash the laundry? 4 hours? I don't think so. 2 hours, yeah. 4 periods. Each period is half an hour, 2 hours. So if you want to compute their utilization ratio, it's dreadful, right? It's very bad. So we only used 2 out of 8 hours. So it's 1/4. It's 25% utilization rate of a washer. So 75% of the time, our washer is sitting there doing absolutely nothing. And this is obviously not a good way to utilize your existing hardware, very expensive hardware. And a better approach would be pipelining, okay, which you can do in real life as well. And the pipelining is shown here in this lower picture, lower diagram. So the idea is that as soon as we are done using the washer and we moved our first load into the dryer, we immediately load the second load of laundry for the second person in the washer. And that's what their diagram would look like. And hey, here's some magic. Instead of 8 hours, it now, yeah, life hacks, exactly. It now takes how long to do all 4 loads of laundry? All 4 people. 3.5 hours, exactly. Wow, that's magic. 8 and 3.5. And if you look at the utilization ratio, for, let's say, their washer, right? It is still used for only for 2 hours, but it's 2 out of 3.5 instead of 2 out of 8. So that's much better utilization that we are seeing. Okay, and then if you if you imagine if we have more loads, then the utilization would be even better, right? Because really there are 3 periods, 1.5 hours that our washer was not used is a constant. If we increase the number of people or the number of loads of this, there 1.5 hours that the washer is not used is only at the very end of our entire operation, and this is gonna be constant. Yeah, we are at our timer, but let me just go back to our slide and well, let's do quickly the animation. So I think it is, and we can do double speed to save time. Right, this is 1, and this is 2. This is the sequential thing, and then when we do it in a pipelined fashion, you see each half-hour period shows which hardware is used, right? So there is a period when all 4 devices are used at the same time, right? So that's the best efficiency that you can ever get. And here are just the formulas. So for 4 loads, we computed their speed up, right? Remember from our previous conversation about what speed up is? Speed up is the amount of time it takes for, in an optimized solution, in a non-optimized solution versus an optimized solution. So 8 hours versus 3.5 hours. So a speed up of 2.3 times. So with 4 loads, we were able to wash our laundry 2.3 times faster with pipelining than without it. And if we actually did it nonstop, so if we have more than 4 loads, the speed up is actually going to approach 4. So n is the number of loads, and you can see what's going to happen with when n is large. So if n is large, you can basically ignore 1.5, right? This this little term in their denominator, and then you have 2n divided by 0.5, and n's cancel out, and then you have just 2 over 0.5, which is 4, which happens to be the number of stages, right? Stage is the hardware, right? Stage is laundry, washer, table, folding table, and the closet. So they're speed up, we can achieve close to 4 if we have enough load, and the load is nonstop. All right, so I went over my time by 2 minutes. I apologize for that, but hopefully this is fine. And we stop here at slide 48, and then we will. Oh, there's a pop quiz. So yeah, let me open that pop quiz. I will keep it open for a little longer, so that even if you have some other class to attend to, you can answer this poll later today. Yeah, I want to push as many polls as I can so that people can earn additional late days. What is n in the second equation? N is the number of loads. So if n is 4, we have 4 people, it's 8, and 0.5 n plus 1.5 is 3.5. So when n is 4, we get the formula that we kind of empirically derived, even without knowing any math. But yeah, n is the number of loads, or the number of people who are doing their laundry. All right, that's all that I have, folks. Thank you very much for attending this lecture. Hopefully you liked it, and yeah, pipelining is exciting. We'll look deeper into pipelining and all the problems that arise there. So you're probably going to appreciate the simple data path control, because what we are about to start is going to be just slightly more complicated. Well, thank you. Enjoy your weekends, and see you on Tuesday. Have a good one, folks.